last time you did an impedance of an inductor, right? What was impedance? Resistance, right. So we kind of refer to resistance in electrical engineering basically as impedance. Resistance can be in different forms. The easiest one was what you had already seen in, heating elements and things like that. The other one was an inductance that you see an inductance in magnetic producing fields. Now is a capacitor. Have you heard of the word capacitor? Yeah?
Yes.
Right. So those of you who've done physics might have seen this. What does a capacitor do? Yeah. Holds a charge. Right. It holds a charge. It has the capacity to hold the charge, and therefore then it releases it when it is necessary. In alternating current AC, we use the capacitor, and then that becomes part of the circuit. So what is an impedance of a capacitor? A capacitor in electrical engineering is shown this way. So by showing this, then obviously you're talking about the resistance, and then for that resistance, you need to see a terminology like this. Now, again, this is under the purview of the complex numbers. And the reason is, why do I have to learn complex numbers? Well, here it is. In electrical engineering, when you're doing electrical circuits, you will get to something like a capacitor. Then the resistance or the impedance of the capacitor is shown as 1j omega c. Now the c here is actually your capacitance, and we're talking about what capacitance is. What is that omega? You remember omega? Yeah.
Angular frequency.
Angular velocity, not angular frequency. Angular velocity, right? But which is dependent on the frequency. We'll talk about that later on. So and then J, what was J? J, yeah?
Angular position.
Angular position, but in this term is a complex value, which basically we talked about the X and Y. J represented the Y-axis. And then at the same time, because it's a complex number, J is equal to square root of -1, right, square root of -1. So in this case, we show the capacitance as C as 20. What is that strange character there?
Micro.
Micro, right. What micro means?
10 to the -6.
10 to the -6, right. 10 to the -6. What is 10 to the -3? Milli, right. And 10 to the -9. Right, so we learn all that. So in this case, we say 20 micro F. Now F is farad, right? Again, another unit. These electrical engineers, they think they're so smart and they name everything after themselves. So farad actually is after the name of a person called Faraday. So we use F, micro F. So whenever in engineering you want to really deal with problems, it's always better to use the actual unit, farad, instead of using the micro, because later on when you are doing the mathematical manipulations and calculations, when you want to convert it into a proper unit, then you may run into difficulty. That's why I'm showing 20 microfarad as 20 times 10 to the -6 F, right? So if it was a microfarad, I would have said 20 times 10 to the -3. And then show it as the actual value. So if I want to replace it in this equation, so F is 60 hertz. What was hertz? Hertz? What does hertz mean? Yes, cycle per second. Cycle per second. Cycle means one full circle. One full circle. The circumference of a circle is one cycle. So when we say 60 hertz, means 60 cycle per second, which means 60 rotation around the circle per second. So that becomes an angular velocity. So the omega, you see that it is 2 pi f. Why did we say 2 pi? 2 pi is the circumference of the circle, right? It's one cycle. So when I say 60 cycle, all I have to do is 60 times 2 pi. So suddenly from hertz, it becomes a radian per second. And that's what we usually use, radian per second. That's the angular velocity of this. Now this is an alternating current, and later on you will see an alternating current moves like this in a sinusoidal or in a circular fashion. So in this case, if I want to find now the value of impedance, all I have to do is just put the values of omega and C in there, right? So in this case, Z is going to be simply 1j omega C. So now we have found the value as 132.6 over J. Okay? Why is it that suddenly everything from below went up? Why do you think that happened? Yeah.
Because it was to a negative power.
Right. You see, 10 to the minus 6 is actually the determining number. It's making that value in the denominator so small that when 1 is divided, that very small number becomes 132.6. You don't believe it, you can do it on your calculator. So basically, what kind of a number is that? Is that a real number? Because of that J is a complex number. It is a complex number, but we're not used to having J in the denominator. So what do we have to do? What do you think we have to do? Yeah.
Can you just raise J to negative 1 power?
If I put the J as a negative minus 1 right here, would that change?
No, we rewrote it as 132.6 J to negative 1.
Okay, well, so what you're saying basically, you're saying that what we need to do in order to simplify it, we have to multiply by 132 over J by J over J. What is J over J? 1, right? So if I'm multiplying, and then what I have at the bottom is J squared, right? J squared. And what I have on the top is J. What is J squared? Because J was the square root of minus 1, right? So J squared is simply minus 1. So what happens here, what do you think would be the value of Z? What do you think the value would be here? Yes?
It would be negative 132.
Absolutely, you're absolutely correct, because J squared is minus 1, and therefore that would be the value of your impedance. And the unit for impedance is ohm, because it's actually a resistance. Okay? So now we found the impedance of a capacitor. So far what you have learned, you have found the resistance, or simply an impedance of a resistor. You've found an impedance of an inductor. And now you've found an impedance of a capacitor. 3 elements in an electrical circuit. Okay? In one case, the resistor, it was simply a real number. But in case of the inductance and the capacitor, they are complex values. So what happens then is that if we now create a circuit like this that has a resistor as an inductor and a capacitor, right? These 3 things that you have seen so far. So when we have an electrical circuit like this in series, what do? We simplify the circuit. How do we simplify it? These 3 elements that we have, right? We simply add them to each other. So if you want to have an equivalent, and again, this has got nothing to do with electrical engineering yet. You will see it, but what I'm trying to show you is that the math you learn in a complex numbers has an application right over here. So if you are given an electrical circuit like this, which is very, very common, in fact, if you go back about 40 years ago, you could have actually physically see this. Because if you opened up in a transistor, a radio, or a vacuum, TV, you would have seen the actual resistor, inductors, and capacitor. Now, all of these, right now, are in an IC, an integrated circuit. In other words, they are so tiny, you gotta put it on the microscope, but they would still behave the same way, because it is an electrical circuit. So if I have a system like this, what I need to do is, I need to basically find an impedance for this, which would be equivalent to what we have over here. Okay? So far, you have seen this individually. So what we need to do is, we have to replace the values for each one of them. In the case of a resistor, Z of R is simply equals to R. Is that a real or imaginary number?
Real number.
Real number, right. So then the next thing is, what is the impedance of an inductor? Do you remember from last time? What is an impedance of an inductor?
C plus J omega L.
Do you remember that? What was the unit for L? L.
Henry's.
Henry, right. We're just going to go through your names, your friend's name, you'll find it. Henry, right there. So the next one is the impedance of a capacitor. And the units for C?
Faradays.
Faradays, right. And then Faradays, actually. Faraday is the person who invented it, but we just say Faraday. Omega, what is omega?
Angular velocity.
Angular velocity, the units for angular velocity.
Radian per second.
Radian per second, very good. So, now let's say, the units that we have used before. Find Z if R is equal to 100, L is 0.025 Henry, and the capacitor is 20 microF, and frequency is 60 Hertz. Everything that you have done in the previous examples, you already have the answers, right? You already have the answer. So the next thing is, what is ZL? In this case, from the before, ZL was 9.426 J, or J 9.426. We put the J behind because we want to do what? We want to show that this is a complex number, okay? And we also want to make sure that you don't get it confused with something else that had a J. Do you remember what had J?
Joules. Vectors.
Don't go that far. I mean, you're too smart to go to Joule. But no. What was that?
Vector.
Vectors, right. I and J, right? What was the difference between that J and this J? The hat, exactly. The hat that created the vector, right? So we already have this. We have the Z of the capacitor. All we have to do now is put these values in there to have an equivalent impedance. I think we got to take the whole class, honestly.
Okay.
Yeah. So take care. Yeah, we was going to cover the whole thing. I want to cover this and then finish it up. So
Yeah, may I just tell them that I've updated the notes for today's class, they could look at it, because it's going to be in the exam next week, so they could work on it this week.
all right, you mean the one that you haven't covered?
Yeah, but I'll cover it
On Monday.
On Monday, but
Yeah,
if they
but
want
they
to
can
look at it.
work on it ahead of time.
Yeah, there are additional MATLAB codes, everything is posted for you, but
Yeah.
under the same links.
But he's going to cover it on Monday, and then your exams are Wednesday. If you want to study over it, you obviously have all of it. Have you seen the notes, by the way, on the blackboard? Is that helpful, or are we wasting our time? Oh,
Very, very.
good. So we put the Z's there, right? All we have to do is just replace the values. Now, you've already found this in the 3 previous examples that we did in the classroom. So all I have to do now is put the values. ZR, which is the 100 ohm, J 9.426, and minus J 132.6. What is the unit of this? Z? The unit? so if we want to show it like that, is it easy to do? Obviously, yes, because we have a real number and a complex number, and by doing that, and this is how we represent it. 100 minus J 123.20. So the impedance of a circuit like this is that a real or a complex number?
It's complex.
Complex, yeah, because it has J, right? Whenever it has J, it's complex number. So have you ever heard of the term ohm meter? Ohm meter? Right, yeah, it's an instrument. The electrical engineers or anybody you want to work around home, you want to measure the resistance of an item, you use something called an ohm meter, which is part of a bigger unit, which is what definitely called potentiometer. Okay, some form of a meter that you can buy in Home Depot, and then you put it. So, but it's ohm meter, and the ohm meter doesn't give you a complex number. It will just give you a number, right? A value. So what we are saying here is, although this impedance is a complex number, but it has a magnitude, right? It has a magnitude here. How do we find that magnitude here? How do we find it? What is the magnitude of a complex number? Yes?
The square root of 100 squared plus the square root of...
Right, so basically square root of the real part plus the imaginary part. And that's the magnitude. So although the number is complex, it has a magnitude, and that's what you are measuring. The only thing is that when you have a complex number, it has something we know as phase, right? A phase angle. You don't need to deal with that now, but when you will eventually get to a point that you say, okay, these two systems have a phase difference, or a phase drop or something. Those are the terms that comes from the complex nature of the number that you're dealing with. So in this case, if I want to find if I want to describe it in a polar form, now in what form is that? Rectangular form, right? So if I want to find it in a polar form, what do I have to do? Okay, so the first thing is the magnitude of z, right? What is the magnitude of z? We just heard. It was simply a square root of that. So that's what you are measuring with an ohm meter. So if I want to find theta, what do I do? Yes?
Tan 2 of y over x.
Right, so y is the what? What is the value of y?
Negative 123.2.
That's right. So basically, in order to find theta, we have to find a tan 2. Well, I'm glad that most of you are getting it now. Right? Very easy. A tan 2 is that minus 50 degree point 93. So if I want to show it in the polar form, I show it this way. Who does not understand this one? So we have learned that we can show it in the rectangular form. We can show it in the polar form. What else can we show it as? Yes?
Exponential.
The exponential form, right. So in the exponential form, we show it this way. I didn't go through that calculation again because everything that you use in the exponential form is similar to a polar form. So one might wonder, well, why the heck I have a polar form and then exponential form? We'll see that in a second, and why we are doing all of this. So far so good? All right. So let's look at this. Let's find the value for a system like this, right? We want to find a voltage for the following circuit, I is 0.1 angle 30 degree amp. So, do we know how to do it? Yes, yes, who do we know? Do we know? How do we do this? In every engineering problem that you will get, this is something that you have to remember. Start simply, but finish completely. Remember that sentence. Start simply and finish that completely. Now, when I'm looking at this, you already know V is equal to what?
Current times impedance.
What's that?
Current times impedance.
Which is I times Z, right? What do we call that voltage law? Huh?
Kirchhoff's law.
That's right, Kirchhoff's law. Did we see that anywhere in my lectures?
Yeah.
Or was that the first session, I think, right? Kirchhoff's law. So in this case, what we need to do is find, first of all, the equivalent impedance. Now, we have resistor, and we have, what do we call this guy? The coil, what was it called?
Inductance.
Inductor, right. We had a resistor and an inductor. For the inductor, basically the impedance is the resistor plus JXL, right? And in this case, is simply 30J ohm. Now you notice that for the inductor, we no longer said omega, we did not no longer say henries. I just gave you straight number for the ohm of that inductor. But because it is an inductor, it is already a complex number. So what we are giving you here, this 30 came from what? Came from, what's that? L times omega, omega L. So omega L is just simplified to 30. So you don't need to look for frequency anymore because I'm giving you exact number right there. So is our impedance a real or a complex number?
Complex.
Complex. So if I'm, so the next thing is, I want to find out the V, which is IZ, right? Now, is I a real or a complex number? Or how do I show this I? In what form am I showing it right here? Yes. Polar. So what do I have to do here? So, this is what we want to do. Now I'm going to show it in two different forms. I'm going to do it in a rectangular form and a polar form. And the objective of this exercise is to show you that, of course, there's not one way of solving this, but then if we want to do it on a rectangular form, well, I have to describe I in a rectangular form because Z is in the rectangular form, right? So how do I do it? Is 0.1 cos of 30 degree times J sine of 30 degree, which turns into a real or a complex number. Complex, right. So my I is complex. We already have Z, which is complex. So all we have to do is multiply the two. Do you see that? I have I complex, Z complex, and then I have to multiply both of them. Do you follow right now? What did I do? All I did was I replaced for the value of the current, or I. You don't have to remember it as current, just simply I. and then the value of impedance as Z. So when I multiply these two complex numbers, what do you think the result will be? Real or complex? Complex, most probably, right? So in this case, this is what I get. 0.0866 times 100 is 8.66. 0.0866 times 30 is 2.598, and then they have a J. 0.05 J times 100 is simply 5J, and then 0.05 times 30 is 1.5, but then J squared. What is J squared? Minus 1, right. J squared is minus 1. So that's why the J squared converts into a real number. So what I have is 8.66 minus 1.5, and then I have 5 plus 2.598. So if I put it together, I should easily find that my voltage is 7.16, which comes from that 5 and the from 8.66 minus 1.5, and then 7.598 volts. Is that a real or a complex number?
Complex.
Complex, right. So if I use something called a voltmeter, have you heard of a voltmeter? Again, I don't get a complex number. What do I get? I'll get the measurement of the magnitude, right? A measurement of the magnitude of this voltage, which comes from where? If I want to find the magnitude of this voltage, what do I do? What do? I have a complex number, I want to find the magnitude. Yes?
Take the square root.
Absolutely, like any other complex number. Any other complex number. If you want to find the magnitude, all you have to do is just square root of the squares, summation of the squares of the different terms, a real imaginary. So this was done under the rectangular form. So if I want to do it on a polar form, basically this is I'm giving you the actual in a polar form. The magnitude and then the angle. How did I get the angle?
The arctangent.
Arctangent to of these two terms. Okay? So I showed it in the rectangular form, and I can show it in a polar form. So, but I'm now going to use the same thing, but then this time I'm going to use the polar form to do all of this. So I had the current in a polar form, so what I have to do is I have to describe Z, which was originally in a rectangular form, in a polar form. Do you see how I did this? You can see that easily I just showed the polar form in an exponential format. Alright? So in both cases, I can show the polar and exponential next to each other. They're identical. One is an exponential, the other one is a polar form. So now I have the impedance and I have the current in a polar form. So now I want to find out the voltage. What do I do? Come on, ask questions. How did I get that? Right? Well, number one, we already had it. I gave it an example. I said it was 0.1 and 30-degree amp. Do you remember? In the description of the problem.
My question is,
Yes.
if they're both the same problem, how come you have a different answer on the left and the right?
We're not there yet. This is the voltage, that's the impedance, and that's the current. So I have the current, and I have the impedance. Now I want to find out the voltage. What should I do?
Times up.
Yeah, V is equal to I times Z, right? So I have the I have the Z. Both in the polar and exponential. So I have to multiply these two. Ask me question, because if you don't ask me question, that means you are 100% clear. Come on, if you look at puzzled, what am I doing here on Wednesday afternoon? You know, I could be out there enjoying the sun. Ask me question. Do you understand? V is equal to I times Z. Same as that. So all I have to do now is put these two in there and see what happens. Okay? So, I've shown it two different ways. One, I've shown it in the polar way, and the second one I've shown it in the exponential way. They're identical. They are identical. Okay, so let me ask you this. Look at the first one. If I want to multiply that, how do I do it? Yes.
You would do 0.1 times the cosine of 30
Uh-huh.
plus j sine of 30 times 104.4 times the cosine of 16.7.
Right. So that's basically what you're doing over there. You're converting polar to rectangular. I don't want to do that. What I want to show you is this is very simple. If I am, for example, multiplying these two, I have the magnitudes right here, and I just simply multiply them. And the other one is E, when you are multiplying two exponential number. So when you have, okay, as usual I have nothing here. 2 to the power 2 times 2 to the power 3. What is the answer? Yes. What did you do? You simply put the 2 and then add the 2 plus 3. Exponential, the same. All you have to do is just add the angles. So multiplication is much simpler. In the polar form, we just simply multiply the magnitude and add the angles. In the exponential, we multiply the magnitude and add the angles. Exactly the same. Do you follow? So in this case, do I get the same answer? Now here's the magic. Look at all this thing that I did over here. And look how simple that multiplication was. Much simpler. Okay? So when you get to a point where you have complex numbers, and then you have multiplication or divisions, or when you have simple additions, you can use different methodologies. We got the same answer by using the exponential format, where in this case, look how much we had to do in order to get that answer. The chances that we make mistakes is very high. Okay? So what do we do here? So we got to make some conclusions. Conclusion number one, adding complex number is easiest in rectangular form. just add the real and imaginary part. So you have two Z1 and Z2, and you want to add them or subtract them. All you have to do is just add or subtract the imaginary components of your complex numbers. Very simple. Number two, multiplying and dividing complex number is easiest in a polar or exponential form. In this case, you simply multiply or divide the magnitudes and add or subtract the angles. So there is your answer. Why do I represent complex number in different forms? Because different solutions require different methods. Okay? Any questions? You have a question in the back? No? So, have you heard of a term called complex conjugate? Complex conjugate. Complex conjugate is simply the complex number, just the sign on the imaginary side has changed. This is called complex conjugate. Why do we do this? Because again, in different engineering problems, you look for the conjugate of the number because it represents a different system. The nice thing about the complex conjugate is that by multiplying it, you get a real number. Multiplying a complex number by its conjugate will result into a real number. How do we do that? A plus JB times A minus JB is A squared minus JB squared. Obviously, JB squared is minus B squared. So minus B squared plus A squared is A squared plus B squared. Do you follow? So that's the nice thing about the complex conjugate, which in that case basically means the magnitude of this new vector or complex number is going to be real. And that's a term that you will remember for the rest of your life, that a complex number multiplied by its conjugate number is equal to the magnitude of that complex number squared. Okay? So, if I have a complex number and I want to find a multiplication by its conjugate, all I have to do is change the sign of the j, and in this case c times c squared is simply 25. Now think about it. It's 25, which means a squared plus b squared. So if I go back to the original number, which is 3 plus 4j, or j4, what was the magnitude of c in that number? What is the magnitude? How do I find the magnitude of c over there? Square root of 9 plus 16, right? Square root of 9 plus 16 is what? Square root of 25. What is the square root of 25? 5. So there you are. A complex number multiplied by its conjugate is square of the magnitude of the complex number. So some final notes in the polar form. I want to show you that we have a complex conjugate in a polar form. If I multiply them, it's 5 angle 53.1. The other one is 5 angle minus 53.1. So if I want to multiply these two polar, what do I do? These polar numbers, what do I do? Yes? Add the degrees, and what do we do with the real part? Multiply, right? So it becomes 5 times 5 is 25, and then simply add the angles, which is 53.1 minus 53.1, which is 0, and therefore the result is a real number. Same thing. So use the polar form instead of rectangular form and got the same answer. Alright, so that basically wraps up the complex number. By now, you then must have an appreciation that a complex number can easily represent an engineering problem. There are many ways that you can use complex number to manipulate or represent an engineering system. How many different ways we can describe a complex number? 2. What are they? Rectangular and polar. Do you agree? 3. Somebody said 3. Exponential. Right. Polar and exponential are almost identical. Now, exam next week basically will be covered until next Monday. Whatever you cover by Monday, the exam will be there. And then try to be here on time. So we will start sharp at noon, and then of course watch the go through the blackboard, find out exactly what is required or what you're allowed. But you are allowed to bring one cheat sheet. Okay?
Wait.
How big?